All right, guys, for those thinking that you've already seen this, you absolutely have. It's just showing you the equation again. The sooner you guys get familiar with these equations and the each one of these variables, what they actually mean, the better off you're going to be. Again, p squared plus 2pq plus q squared is the main equation that you're going to be looking at. However, at times you are going to also look at p plus q equals 1. Um, just rarely, doesn't happen often. Most of the time, this is your bread and butter. What you need to understand though is what are you trying to find? Depending on what you're trying to find, it'll dictate which one of these equations you want to look at. But you have to understand again what these variables mean. P squared is the frequency of the homozygous dominant gene or homozygous dominant individual. So if you have a capital B, that's homozygous dominant, you are counted in that p squared group. If you are looking for the homozygous recessive, so the lowercase b, in this example, I didn't even tell you what the trait is, but this example, you're looking for the q squared equivalent. This is the frequency of the homozygous recessive individuals. So if you are lowercase b, you fall within that category, within that camp, and you will be represented with this q squared. Okay. If you're looking for the heterozygous, those people that are capital B, lowercase b, those middle ground people, those are the 2pq. Okay. And then of course, if you're just looking for the frequency of the dominant gene, the capital B, that's going to be P. And if you're looking for the recessive gene, the lowercase b, that's going to be Q. And it makes sense, guys. I hope it does. If it's not, I hope it's starting to. Hold on, let me go get a marker, which apparently I don't have. I hope it's starting to make sense. I hope that you understand that, like, if this, let's go back to this P here. If this is capital B, blue is probably not the best choice, but, bear with me. Sorry, a little something caught my throat. It's not corona. All right, if this is capital B, that's the dominant allele, okay? What is the homozygous dominant individual going to have? It's going to have, homozygous means the same, dominant means the dominant allele, so it's going to have a capital B, capital B. Or you could say, if P represents B, you could say a P squared. Because what's 2 times 2? It's 2 squared. Okay, it's the same thing. So this is how we get from here to there. If you're homozygous recessive, or if this is the recessive allele, that's a horrible lowercase b, bear with me. Then obviously if you're homozygous recessive, you're going to have lowercase b, which means that if b equals q, you're going to have q squared. B times b is going to be, in this case, q squared. Okay, if you have both P and Q, okay, if you have a capital B and a lowercase b, meaning you're heterozygous, then we represent that with 2 PQ. Okay, hopefully that's starting to make sense. Hopefully you guys are watching these videos, and the more you hear this, the better off you're going to be. All right, so continuing on, again, you've already seen this slide as well. This just says that it all depends on what it's asking. If the question asked, what is the frequency of an allele, didn't ask for an individual within a population or something like that. It's talking about the frequency of an allele. That's the key word there, the key phrase. Then it's asking for P or Q. Okay? Not P squared or Q squared, but just P or Q. The frequency of that particular allele. P, of course, being the dominant allele. Q, of course, being the recessive allele. However, if it asks for something else, if it asks for the frequency of an individual, okay? Sometimes it'll say the individual organism in a population. Again, key phrases. That the more of these you do, the better off you're going to be. Then it's asking for the homozygous dominant individual, the P squared. It's asking for the heterozygous individual, the 2PQ, or the homozygous recessive individual, the Q squared. Okay? You have to figure out for yourself which one it's asking for. All right. That finally brings us to this. I don't know. I think I'm going to show you an example today. but I'm not going to make you guys go through them on your own. I want you guys to practice. Okay, so anytime I show you an example, just like in math class, okay, and I think I've said this before in this class, or at least in others, in math class, if a teacher is doing a problem on the board, he or she is not doing it for their own convenience. Okay, Mr. Cohan, it's that big dude that you guys all think looks like me, who probably misses you guys dearly. He is not doing math problems up on the board because he needs to figure out how to do them. Right? He knows how to do math, I would assume. Okay? He's doing them so that you guys can see how to do them and do them with him. So if I was teaching math, it would be imperative, and I'm sure it is for Mr. Cohen's class or anybody else, Miss Aries, whoever it might be. Whatever you guys do, or whatever he does rather, and whatever I do on the board, you guys also have to do. So make sure that whatever examples we do, and we're going to stop and do one of these here in just a second, make sure that you guys are doing them with us. That is what I've asked for today, by the way, when you guys go and you upload your notes. The only thing that I want is practice problems for the Hardy-Weinberg. So if we do one practice problem today, all you have to do is take a picture of that one problem and upload it. If we do two, take a picture of two problems and upload it. I doubt we're going to do any more than maybe three at the most. I think we're only going to do one. So I'm going to play this video because this is a great resource. By the way, you can find this. Sometimes listening to me, I'm sure, is just difficult. So if you want to listen to what's this dude? Bozeman Science. That's the YouTuber. He's actually a teacher that started to do videos, and now he has a channel that's really, really good. All of his science stuff is really good. You guys have watched some of it with evolution already. But if you guys want to watch this again, go to Hardy-Weinberg Problems, Bozeman Science. Type that into YouTube, Bozeman Science / Hardy-Weinberg Equilibrium or Equation or whatever it might be, something along those lines. You will find this thumbnail, hopefully. You guys can watch this again, or you can just, actually, this is silly, you can just rewind this video and watch it again if you'd like. I give all the credit to this guy. Obviously, this is not my video. So let's go ahead and watch this, and I'm going to stop it probably a couple times.
Hi, it's Mr. Anderson, and in this podcast, I'm going to hopefully show you how to solve Hardy-Weinberg problems. Here's Hardy, here's Weinberg. They came up with this wonderful idea of Hardy-Weinberg equilibrium. It's used by geneticists and evolutionary biologists, but little did they know they would plague biology students forever as they try to solve these problems. And so this would be a typical Hardy-Weinberg problem. We've got 16% of the population unable to taste a chemical, and they're asking a number of questions like how many people are heterozygous, what's the allele frequencies. And when I have students who struggle with this, basically all these terms are kind of swimming around in their head and they have no idea what's what or where to even start. And so I want to kind of go back to basics and show you what a gene pool is, and then show you how to solve some of these problems. And so let's start with a sample population. Let's make this population really, really small. Let's say we have 10 people. So we've got 10 people here, and half of them had red hair. And so to have red hair, you have to have two red alleles. So this would be a person with red hair, red hair, red hair.
Because red is
hair,
recessive.
Red hair. So half of the people have red hair, and then half the people don't. And so this would be somebody who maybe has black hair, or this could be somebody who has blonde hair, or it doesn't matter, but they don't have red hair. And since it is a recessive, you have to have two copies of it. Okay. So this would be the population, and this would be their phenotypes, physically what they look like. But if I take all those genes...
That is not what I wanted to happen, sorry. Let's find that again.
Don't have red hair.
But I did want to pause it. That was my main objective. I wanted to show you guys what he is trying, or what he's demonstrating here. I say trying, but he's doing a great job. This is the gene pool because it represents all the people in the population. Every one of them that has the homozygous recessive trait for red hair. You can call that, I don't know, lowercase r, lowercase r, well, whatever you want it to be. But this individual has lowercase r, has two alleles that show the recessive trait, which is red hair. So if they have both of them, that makes them homozygous recessive. So they, of course, show their phenotype is red hair. Again, guys, go back through your notes, or if you're having trouble, email me or send me a message somehow. If you're having trouble remembering what homozygous recessive, homozygous dominant, phenotype, genotype, what all those terms mean, that was from genetics. It was from the last chapter. So make sure that you guys look back over that. So this individual is homozygous recessive, which means that their phenotype is red hair. This individual is is heterozygous. They have the recessive allele and the dominant allele, which means that they are going to show their phenotype is going to be the dominant allele, whatever that is. So let's say it's black hair. So these people have red hair. This person has black hair. Even though they're carrying the trait for red hair, they are demonstrating black hair through their phenotype. Okay, so he just wants to show you what a gene pool is. A gene pool is all of these alleles kind of mixed up into one area, but he's going to go through that with you.
Since it is a recessive, you have to have 2 copies of it. Okay, so this would be the population, and this would be their phenotypes, physically what they look like. But if I take all those genes in a population and scramble them up and put them in a pool, then it becomes a gene pool. Now they're not associated with one individual anymore. And so basically, this is a gene pool. And so there are 2 values that I want to throw out. The first one is P, and the second one is Q. P is going to be the allele frequency of the dominant trait. Okay, so what's the dominant trait? That's going to be this non-red. And so I'm going to say 1, 2, 3, 4, 5, 6. There's 6 of them. And there are 20 total alleles here. There are 20 total genes. And so our p-value would be 0.3.
I did it again. Okay, I'm sorry. I'm going to figure out why it keeps... I want to pause it, but unfortunately, it doesn't want me to pause.
Hi, it's Mr. It's going to be 0.49. Let's do that again with the blues. What are the odds of me pulling a blue out and then a 3? And so now how do we figure out the Q value? Well, the Q value, I could count up all the red ones.
Okay, so I just want to kind of talk about what he just did there. Finding the p-value. Hopefully you guys are following along. I know I've had to stop several times and find it in the video again. But he took, remember, we're trying to find allele frequency here. So this is P and Q. P, of course, stands for the dominant allele, the dominant trait. Q stands for the recessive. So let me get rid of this guy. So what he did there, when we're finding a frequency, we're not just finding a number, we're finding a percentage. We're always finding a percentage. But how do we write a percent? We write it as a decimal. So we're finding the fraction of how many we see within the gene pool. So with P, we're talking about the dominant trait. Of course, he counted them up. He found that there were 6 out of the total 20. That would be like, if 6 people out of the class had a certain trait, that sort of example. So he took 6, and instead of just saying 6, that P is the value of 6, it's not. Remember, we're looking for a percent. He took it out of 20. So 6 out of 20 is a 0.3 or a 30%. And that's how he got that 0.3 value. He's going to do the same thing for the Q. Obviously, which one's going to be higher? The Q is going to be a lot higher because there's a lot of the recessive trait. Remember, Q is equal to the frequency of the recessive trait. So what he's going to do is he's going to count all these up. I don't know how many there are. I guess you could count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 out of 20. Whatever 14 divided by 20 is, that's going to be your Q frequency.
It's going to be 14. And then I divide that by 20, and it's going to be 0.7. Another quick way to do that is if you figure out that this is 0.3, P plus Q will always equal 1.
Really important
so
there.
I could have just taken 1 minus 0.3, and that would have given me my Q value. And so what does this mean? Well, in a gene pool, this means that 30% or 0.3, be cautious of percents because they can get you in trouble when you're solving problems. But 30% of the individuals are going to be, of the genes, are going to be of the dominant, and 70% are going to be of the recessive. Now, if you know anything about genetics, we can figure out where the rest of the Hardy-Weinberg comes from. So what are the odds if I were to just grab one of these, if I were to just randomly grab one of these genes out of the gene pool, what is the odds that that is going to be recessive? In other words, what are the odds that it's going to be red? Well, the odds would be 7 out of 10. What are the odds if I pull 2 of them out that they're going to be red? Well, knowing anything about the law of multiplication, that's going to be 7 out of 10 times 7 out of 10. And so that's going to be 49 out of 10, or that's going to be 0.49.
You meant to say 100 there.
So grabbing 2 of the reds, it's going to be 0.49. Let's do that again with the blues. What are the odds of me pulling a blue out and then another blue out? It's going to be 3 out of 10 times 3 out of 10. And that's going to be 9 out of 100, and that's going to be 0.09. Okay, so for me to get 2 of the recessive, it was 0.49. For me to get 2 of the dominant, it's going to be 0.09. So what are the odds of me pulling out a blue and then a red? Well, to do that, it would be a 7 out of 10 of the red times a 3 out of 10 of the blue. So that's going to be 21 out of 100. But I don't have to necessarily pull out a red on the first time and then a blue on the second. I also could do it by getting a blue on the first time, 3 out of 10, times 7 out of 10. And so that would be a 21 out of 10 out of 100. And so I have to add these two because I could get a red and a blue one in 2 ways. And so when we look at the equation for Hardy-Weinberg equilibrium, let's go to that. Where do we get this p squared, 2pq, q squared? P squared is basically taking the allele frequency of the dominant. When we were solving this problem, that was 0.3, and then we simply square it. And that's going to tell me how many individuals are homozygous dominant. In other words, they have one of each of the genes. What are the odds of me doing this one? In this case, our recessive value is 0.7 squared, so that's going to be 0.49. That's a homozygous recessive individuals. And then the heterozygous individuals are going to be 2 times p times q, because you could get it either red-blue or blue-red, so either of those. And so this is where this term comes from. And so basically, even though I may have lost you at this point, the big thing to remember is that if they talk about the allele frequency,
Really important here, guys. Listen.
then they're talking about the p-value and the q-value. If they're talking about individual people or individual organisms or individual phenotypes, then they're talking about p squared, 2pq, and q squared. Because it's vital when you're trying to tackle one of these problems that you know what you're given on day 1 or on the first step. And so let's try this problem again. So what does it say? It says, let's break down this thing. 16% of a population is unable to taste this chemical.
Okay, so we're going to stop him, and we're going to see if Mr. Eddie remembers how to do these really well. We're going to go through this, but I want you to go through it with me, okay? Please do not sit there and think, okay, well, he's talking now, I can just kind of shut down. This is going to be one of your example problems. This is exactly what you're going to see with these types of problems. It says 16%, so it always gives you some information, and then, of course, it asks for some information. 16% of the population is unable to taste the chemical PTC. These non-tasters are recessive for the tasting gene. Okay, so we're talking about individuals, right? We're talking about people. These non-tasters, that's an actual person. What percent of the individuals of the population are tasters? Okay, well, that one's kind of easy, right? Hopefully it is. It says 16% of the population are non-tasters. Okay, so what percentage of individuals are tasters? This one actually has nothing to do, this problem here, number 1, has nothing to do with Hardy-Weinberg. It's just kind of a common sense question. And believe me, people get it wrong all the time, because I will ask you similar questions to this. But if 16% can't taste the chemical, how much of the population can? Well, you take 100%, right? That's the whole population, and you subtract the 16, and just for sake of me not getting anything wrong, it's going to be 84. But I'm going to get my calculator out, just so I have it. I want to make sure that you guys are getting the right information. But yes, 100, like I said, it's going to be 84. 100 minus 16, you get 84%. Okay, so 84% of the population, this is the answer to number 1, can taste this chemical, whatever, PTC. So number 2, it says, what is the frequency of the dominant and recessive allele? Okay, notice what it asks there. It says frequency, okay, of the dominant recessive allele. The key word here, more than anything, is frequency of the allele. So, are we going to look, let me go ahead and write up on the board p squared plus 2pq plus q squared equals 1, and our other equation, p plus q equals 1. Okay? This one is for individuals. All of these are for individuals. This one is for allele frequency. Which one does the number 2 ask for? Is it asking about an individual within the population, or is it asking about the allele frequency? I just told you that it says frequency of the allele, so it's asking for the allele frequency. It wants to know what P or Q is, and it's asking for the dominant and recessive, so which one does it want? It wants both P and Q, because remember, P is dominant, Q is recessive. So it wants to figure that out. So how do we do this? This is kind of hard, okay? If I want to figure out what P plus Q is, how do I get that from this information? Well, it tells you something important in the beginning of this problem. It says 16% of the population, that's people, are unable to taste that chemicals. These non-tasters are recessive for the tasting gene. So if they're recessive, if there's 16% of them, okay, which one of these up here, because we're talking about people, we're not talking about these over here, we're talking about people. So which one of these up here represents the recessive individual, the homozygous recessive individual? That's going to be q squared. So if q squared, that's the one we're looking at, okay, because q squared represents homozygous recessive. If q squared equals 16% or 0.16, because you can always change that percent to a decimal, then what does q equal? What do I have to do to find q? If I know q squared equals 0.16, all I have to do is take the square root of that. I end up with q, because it gets rid of that square, equals, what's the square root of 0.16? I have no idea. Let's go ahead and type that in. Okay, hopefully. I just type in 0.16, and I hit that square root sign, and I get, that's what I thought, I get 0.4. Okay, so q equals 0.4. That, and by the way, like I said, make sure that you did that right. I just took the square root of 0.16. Okay? If q equals 0.4, then what is p going to equal? Well, p plus q equals 1. So if I type this in, I could say p plus 0.4 equals 1. If I'm trying to do this calculation, to find p, I subtract 0.4 from both sides. Okay, I'm going to get p equals 0.6. Okay, so now I have the answer to number 2. It's going to be, for the dominant, it's going to be 0.6. For the recessive, it's going to be 0.4. Okay? Again, the first one was 84%. The second one is 0.6 or 0.4. If you wanted to change that to a percentage, this would obviously be 60%. This would be 40%. Okay? All you're doing is you're taking in a decimal, changing it to a percent. All right, then finally it says, what percentage of the population are heterozygous for the trait? Okay, so again, it says percentage of the population. What is the population made up of? Individuals. So it's not asking for P or Q. It's not asking for the frequency of the allele. It's asking for one of these. Well, we've already found the homozygous recessive, but this asks for the heterozygous. Which one of these, P squared, 2PQ, or Q squared, represents the heterozygous? It's going to be 2PQ. So the last one is asking you to solve for 2PQ. Luckily, I'm going to pull that part of the equation out. I'm going to put it right here, and I can solve for it fairly easily. All I have to do is take 2 times P times Q. Luckily, do I have the values for P and Q? Yes, I do. P is 0.6, Q is 0.4. So I'm going to say 2, put parentheses in, put 0.6 times 0.4, and all I have to do is solve for that. So I take, let's go ahead and get my calculator again. I take 0.4 times 0.6. You don't have to, I put this way, but you don't have to like factor it or anything. I get 0.24, I multiply that by 2. I'm going to get 0.48. So 2PQ, or the heterozygous, percentage of the heterozygous within the population, represents 48.48 or 48%. Okay? That's what 2 times 0.06 times 0.4 equals. All right. How do we do? Are we following what is being asked here? what is being given and what's being asked. Again, I don't think these problems are easy, but if you have a good grasp of what is being asked, if you understand homozygous dominant, homozygous recessive, heterozygous, if you understand that these are the individuals and these are the allele frequencies, and you can kind of gather what is being asked, then you can hopefully figure out how to best answer that question. So I'm going to let him go through. Hopefully he can get it done in about under 5 minutes because I'm running out of space on my phone.
Chemical. These non-tasters are recessive for the tasting gene. So if you think you know how to do this, you may want to pause the video, try to work it out, and then I'll show you how I would work it. Pause video. Okay, so here we go. So basically, what are they telling me? They're saying 16% of a population. So are they talking about genes or are they talking about people? Well, they're talking about
That's a key
population.
question.
They're saying 16% of the people are unable to taste it. And so what are they telling me? They're telling me, you know, p squared, 2pq, or q squared. Almost always when you're solving one of these problems, they have to tell you the individuals who are homozygous recessive. And the reason why is if you're dominant for the trait, we can't tell if you're homozygous or heterozygous. So they almost always start with q squared. So they're telling me q squared equals, and now we want to get rid of the percents, we're going to say equals 0.16. Okay, so 16% or 0.16. So now my goal in any problem, even though I haven't even looked at the questions here and what they are, is to get to P and Q. Because if I can get to P and Q, I can solve any problem.
It's very true.
So how do I get to Q?
You can find P and Q,
you're
you're golden.
I can take the square root of that side. I can say Q equals 0.4. I can say P equals 0.6. And now I can just smile to myself because I know I can solve any problem that they ask me with just a little bit of common sense. So I got my P and Q value. So let's look at what questions they ask. Number one, what percent of individuals in the population are tasters? Well, let's use a little common sense. They're saying that 16% are non-tasters, and so that means that everybody else has to be a taster. So I would say 84%. Okay, let's look at the next question. What is the frequency of the dominant allele, and what's the frequency of the recessive allele? Well, the frequency of the dominant allele, we've already solved that. That's going to be our p-value, so that would be 0.6. And then what about the recessive allele? That's going to be 0.4. That's going to be my Q value. So I'm golden so far. Now let's go to the next one. What percent of the population are heterozygous for the trait? So now we have P and Q. We can solve for this. Heterozygous, remember, are always going to be those individuals that are 2pq. So it would simply be 2 times P, which is 0.6, times Q, which is 0.4. So this is going to be 0.24. So I would say the total is going to be 0.48. Or if we're looking for a percentage here, I would say it's 48%. Okay. So the majority of questions you get when you're solving Hardy-Weinberg questions, they're almost always going to start by telling you the individuals who are Q squared. And so if you remember that and it's an individual, then you're going to do well. Let's go to...
Okay, I'm gonna stop it there. We're gonna watch the rest of it next time, and we're gonna continue to do more problems. We only did one today. That's the one that I need you guys to upload for me for your homework, so you guys get some points for this. Hopefully, it's making some sense. If not, let me know, and we'll do the best that we can. All right, guys. Talk to you next time.